Besides crossing over, under, and through land and water, civil engineers have devised ways to harness the bounty of nature. Dams help create bodies of water for drinking and generating power. They also help control flooding and bring much-needed water to arid regions. This is the tale of two mighty rivers, both tamed by technology and tenacity. In the American West, it was the Colorado River, the force that carved the Grand Canyon out of solid rock. In China, it was the picturesque Yangtze, a river closely associated with Chinese history, culture, and daily life. For centuries, both rivers provided nearby communities with much-needed water for drinking, cooking, cleaning, farming, and raising livestock. But the water offered something else: potential energy. It could generate enough electricity to power whole cities like Las Vegas. To do that, dams are necessary. A dam is a structure that spans an entire river and holds back the water. It can release water in a controlled flow that spins turbines and generates electricity. As one of the first major concrete dams, the Hoover Dam was a model for the construction of many other concrete dams, including the Three Gorges Dam spanning the Yangtze River in China. The first step in building Hoover Dam was getting the necessary equipment and materials to the site, a remote, inaccessible, and inhospitable canyon in the desert. Roads and tunnels were built and railroad tracks were laid. A dam can't be built across flowing water, so the Colorado River had to be diverted before construction could begin. Workers blasted 4 separate diversion tunnels through the canyon walls, 2 on each side of the river. These tunnels carried 1.5 million gallons of water per second. At 56 feet in diameter and approximately 4,000 feet long, these massive tunnels were among the largest ever created by people. To make the tunnels, drilling rigs called jumbos were built on the beds of old trucks. Each jumbo held up to 30 men who attacked the rock with pneumatic drills. Men called powder monkeys packed the holes with dynamite that blasted out tons of rock. Simultaneously, men referred to as high scalers hung precariously from ropes hundreds of feet above the river. Using jackhammers, pry bars, and dynamite, they cleared the canyon walls of any rocks that might become loose later. As the diversion tunnels neared completion, dump trucks piled tons of rock and debris into the middle of the river. This created a cofferdam, which kept the construction site dry by redirecting the water into the diversion tunnels. Once the site was dry, construction of the dam itself began. Hoover Dam combines 2 types of dam designs: an arch dam and a gravity dam. Arch dams work well on narrow rivers that provide good side support. A dam made from less material provides the same strength when it is curved or arched, because the pressure of the water on the center of the dam forces the edges of the dam to push harder into the canyon sides. On the other hand, gravity dams are straight. They hold the water back with their enormous weight. Workers built 2 enormous concrete mixing plants at the site. The rock, sand, and gravel needed to make the cement were collected locally, but Portland cement had to be brought in. Railroad tracks and trucks could not reach every point where concrete had to be poured, so they constructed a system of cableways to carry giant buckets of concrete from railroad cars. They poured them into the columns as needed. Although the dam looks like a solid block of concrete, it was actually poured in 5-foot layers in a series of separate columns of varying size. The concrete could not be poured deeper than 5 feet at a time because intense heat builds up as concrete cures. The ingredients in concrete undergo an exothermic reaction when combined, meaning they generate heat. Letting the concrete cool naturally would result in weak concrete, so engineers came up with a solution to remove the heat quickly. They refrigerated Hoover Dam. Workers built a very large refrigeration unit at the site. Engineers cooled the freshly poured concrete by embedding 1-inch steel pipes circulating ice water from the refrigeration plant through them. Upon completion of the dam in 1936, workers lowered a steel gate to plug up the diversion tunnel. The Colorado River's water started to back up, creating Lake Mead. Though it looks like a solid wall, the dam is actually a complex machine. 4 intake towers allow river water to flow into giant pipes, or the original diversion tunnels, that lead to the U-shaped power plant at the base of the dam. There, the water flows into smaller penstock pipes on its way to the water wheels. As they turn, the turbines generate electricity. In China, workers are building the Three Gorges Dam across the Yangtze River. It is the most ambitious construction project in China since the Great Wall was built more than 2,000 years ago. Construction of the main wall was completed in 2006. The dam is expected to be fully operational in a few years. Though 5 times larger than Hoover Dam, the basic building process was much the same. The river was temporarily diverted through a channel, while cofferdams kept the construction area dry. The Three Gorges Dam does not have the distinctive curved, arched gravity design of Hoover Dam. Instead, it cuts straight across the Yangtze River. Three Gorges Dam will create a body of water 577 feet deep and as long as Lake Superior. It will be a major producer of hydroelectric power, serving a huge industrial region in the heart of China. But it will use many of the same principles and innovations invented in the harsh desert canyon of the American West. Getting from point A to point B can be difficult when there's a mountain or body of water in the way. That is, until you build a tunnel. In the tunneling industry, they are called sandhogs, the men and women who do the dirty and dangerous work of holing through mountains, under rivers and seas, and below densely populated cities. They burrow into the ground to build passages that let people and cargo move faster between previously unconnected places. People often take tunnels for granted, but the technology and ingenuity that make them possible are among the greatest engineering accomplishments in human history. The tunnel boring machine, or TBM, revolutionized digging tunnels. This massive steel machine has blades that measure 45 feet in diameter, the width of a tunnel itself. A TBM allows builders to drill through almost any kind of rock, creating relatively smooth walls and without significantly disturbing surrounding soil. This machine does the work of many people, which reduces injuries and other dangers. Although expensive to build and operate, a TBM can cut through more than 12 feet of rock in an hour and operate around the clock. This one is carving a water tunnel in San Bernardino, California. It grinds the rock into gravel and sends it by conveyor belt to waiting trains. The titanium teeth of a TBM can chew through almost anything. Long tunnels may contain many types of rock. The TBM's cutting head can be changed to accommodate them. Tunnel boring machines may make the process look easy, but it isn't. Building a tunnel is a slow and dangerous proposition. Tunneling goes back at least as far as the ancient Romans, but modern methods took hold in 1850 with the invention of the rock drill. In the mid-19th century, the streets of London overflowed with people, horses, and carts. The London City Council proposed building a new rail line within the city to ease congestion. But since most of the land was already developed, there was little room left. In 1860, the council came up with a solution: build it underground.
The railway was built by a tunnelling method which we call cut and cover tunnelling. What you do is you decide where the railway is going to run, you literally dig a trench, You build your railway in the bottom of it, you roof it over and put the road surface back.
It took 3.5 years to build the first part of London's first subway, known as the Underground.
The business about getting tunnels deep under London, in fact, was the technique used was first pioneered by the famous engineer Mark Brunel, who built a tunnel under the Thames in the 1820s.
Brunel invented the tunneling shield, which created space for workers to dig. The South African engineer James Henry Greathead perfected this concept.
Greathead saw what Brunel had done and took the idea and improved it and invented a machine called the Greathead shield, which is still used today.
Tunneling became easier in 1867 when the Swedish chemist Alfred Nobel invented dynamite, which is still in use today. Dynamite brought Alfred a great fortune, which he used to finance the Nobel Prize. The Gotthard Tunnel through the Swiss Alps represents one of the most impressive early tunneling achievements. Built in the late 1800s, it runs 9.5 miles through the mountains. Using dynamite, drills, and other early construction tools, the builders tackled non-stop challenges, including flooding and illness. Many crew members, including the chief engineer, Louis Favre, died during construction. To prevent some of the airborne diseases that plagued the Gotthard project, engineers started using tubes to blow fresh air to the head of the dig. The fresh air forced out the stale, contaminated air. By the 1920s, tunnel building technology advanced with the immersed tube tunnel technique. The Detroit-Windsor Tunnel was constructed this way. First, they dredged a trench under the Detroit River. 9 large tubes, 31 feet in diameter and 248 feet long, were sealed and then lowered into the trench, where divers connected the tubes together. Once securely sealed, the workers continued construction inside. Tunneling technology has improved since its early days, but in some ways it has not changed at all. Most of the original techniques, including cut and cover, are still used by modern engineers. Every tunnel project has its own challenges and limitations. Sometimes even powerful tunnel boring machines get caught between a rock and a hard place. And the only way out is to dig by hand. What's the longest tunnel that you've ever been through? The Brooklyn Bridge, pardon me, was the world's largest suspension bridge when it was finished in 1883. Bridges help us connect land to land. But what about connecting water with water? Whoa! Oh, hey, I'm walking here! Kids. Now, if I could just get to the other ocean here, it would save me months of travel around South America. That's what King Charles V of Spain thought in 1534. But the canal wasn't completed until 1914, after U.S. President Teddy Roosevelt sent thousands of workers to Panama to dig their way across. Canals are artificial waterways built to connect rivers, lakes, or oceans. Some canals carry water to irrigate crops, but the biggest canals carry ships filled with passengers and cargo. The earliest canals were links or extensions connecting natural rivers. One of the first was the Grand Canal of China, begun around 486 BC and finished more than 1,000 years later. It was an engineering marvel of its day. In the early 20th century, another great canal opened, also an engineering marvel. The Panama Canal cuts through 50 miles of dense tropical jungle and solid rock, creating a shortcut between the Atlantic and the Pacific that allows ships to go from sea to sea in just 10 hours. The canal provides ships with a much quicker and safer alternative to the perilous 7,872-mile-long passage around the tip of South America. Every year, thousands of ships are literally lifted across Panama's mountains by a remarkable series of water elevators and artificial channels. A ship entering the canal from the Atlantic Ocean navigates a lock facility of 3 chambers, or water elevators, that raise the ship 85 feet to the level of Gatun Lake. At the other end of the lake, more chambers lower the ship to sea level on the Pacific side. Lifting a massive ship with a mechanical elevator is an enormous challenge, but water does the job easily. The system works like this. The lock facility on the eastern side of the Panama Canal consists of 3 connected chambers. 6 locomotives guide the 65,000-ton ship into the lock chamber. Once inside, the gates close. In the control tower, operators turn valves releasing water from Gatun Lake into the chamber. Gravity pulls water from the lake and sends it into the chamber through holes in its floor and sides. The rising water lifts the ship to the level of the next chamber. The gates, each weighing hundreds of tons, open slowly and the locomotives pull the ship forward. The process is repeated until the ship rises 85 feet above the Atlantic Ocean. Then it's released into Gatun Lake. When the canal first opened in 1914, the size of the locks in Panama set the size limits for shipbuilders. New supercargo ships, however, are too long and too wide to fit through the canal's locks. If the canal is not expanded, it could gradually lose its importance in world trade. In October of 2006, Panamanians voted to expand and modernize the canal at a cost of more than $5 billion. The biggest engineering challenge to upgrading the canal will be building new locks, 3 times the size of the originals. 2 design teams will handle the project. An American team will engineer the canal's new locks on the Atlantic side, and a European team will design locks for the Pacific end. To build the locks in the soft, unstable rock of the canal's Atlantic end, the American team is considering technologies already used on the Monongahela River, one of the world's busiest waterways. Instead of building a massive dry construction site in the middle of the river, the builders of the Braddock Locks and Dam first built sections of the structure on land. Then, they floated them into the middle of the river where the pieces were assembled. A similar method might be used to build the Panama Canal's new Atlantic locks. The canal's new Pacific locks face a different problem: powerful ocean tides. Twice a day, the tides at the canal's western entrance rise and fall an average of 12 feet, putting enormous pressure on the gates of the locks at high tide. Gates for the new Pacific locks must be almost twice the size of the existing Pacific gates. The gates in the proposed design are already in use in a canal in Antwerp, Belgium. They roll into place across the lock chamber, but these would have to be much stronger to handle the high water pressure. Ships entering the Belgian lock are lashed to the lock wall to keep them stable. The water enters through a set of pipes that is simpler and more dependable than those currently used in the Panama Canal. Water is the engine that drives every lock system. But Panama's Gatun Lake does not hold enough water to lift megaships through a larger version of the type of locks used in Belgium. Fortunately, engineers can use a system of holding tanks that recycles water to operate the locks. When a ship on this canal in Germany needs to move from a lower elevation to a higher one, engineers release water from the top lock chamber. Instead of spilling out into the river, the water flows into a nearby holding tank where it's used again. If engineers build similar holding tanks for the Panama Canal's new locks, they might be able to lift and lower megaships with the same amount of water used in the current locks. Bigger locks and modern equipment will keep the Panama Canal working for many years. If the Panama Canal is fully expanded and upgraded, it will change the way many goods are shipped and the way many people travel, just as it did when it first opened.